Hello everyone, and welcome to this video on orthogonal diagonalization. And what you're going to see in this video is something very similar to a previous video that was put out by me on diagonalization of a matrix. Right? A matrix was diagonalizable if you could find a matrix, say P, such that P inverse times A times P was a diagonal matrix, where, down the diagonal of this diagonal matrix, if you recall, were the eigenvalues of the matrix A, and the matrix P that we made was made up of the eigenvectors, the n independent eigenvectors. So what's going to happen today in this video is something very similar to that, but the word orthogonal is there now. Right, so there's a little extra, a little more to it. So let's get into it. So orthogonal diagonalization. So if we're looking at a square matrix, called A, capital A square matrix A is orthogonally diagonalizable if an orthogonal matrix called P, or whatever you want to call it, but I'll use the letter P. If an orthogonal matrix P exists such that P transpose times A times P is equal to D, where D is a diagonal matrix. And equivalent to this, you could also say where A is equal to P times D times P transpose. And again, the reason this is similar to diagonalization, right, is because when you talk about, remember the definition of an orthogonal matrix. An orthogonal matrix was a matrix whose inverse was its transpose. Right, again, I put out a previous video. Again, hopefully you're watching and following along with me. And an orthogonal matrix also has, columns that form an orthonormal set. Right, so each pair of columns under the dot product, right, we'll use the dot product as the inner product here. So in this matrix P, each pair of columns will have a dot product of 0, and it will be orthogonal, and each column will have a unit, a norm of 1, will be a unit vector. All right, so if I take the dot product of every column of P with itself, it's going to be 1. And then we have our, P transpose, which is what P inverse is, times A times P equal to a diagonal matrix. So again, just similar to when we talked about diagonalizing a matrix. All right, and then we would say that this matrix P orthogonally diagonalizes A, or P orthogonally diagonalizes A into D. Okay, and the process for doing this, the procedure for finding this matrix P that orthogonally diagonalizes A, is pretty similar to how we just regularly diagonalize the matrix back in my video on diagonalization. We're going to be finding eigenvalues, and then the eigenspaces corresponding to those eigenvalues, and bases for those eigenspaces. The major difference, though, is we're not going to just use those basis vectors. We're going to, use those. We're going to transform those basis vectors for the eigenspaces into an orthonormal set of vectors, and then we can construct an orthogonal matrix, because again, I'll say it again, an orthogonal matrix, the columns form an orthonormal set, right? So I can't just use any old set of vectors, right? All right, so the next page, I'm going to basically describe to you a condition under which we can tell that a matrix A is orthogonally diagonalizable. When can I do this? When can I take a matrix A and find an orthogonal matrix P such that this happens? So this is a statement of something called the Spectral Theorem. I'm not going to prove this. This is not the point of the video to show a proof. It's just I'm going to make this statement, and then we'll move into how do I perform orthogonal diagonalization and get into some examples. So again, suppose A is some n by n matrix with real number entries, belongs to R n by n, or M n by n if you see it in other books. So first statement is that the eigenvalues of a symmetric matrix A, right? So if A is symmetric, the eigenvalues will all be real numbers, right? So you're not going to end up with imaginary or complex numbers, complex eigenvalues with an imaginary part. They'll be all real numbers. And if you recall, what a symmetric matrix is, any matrix that's equal to its own transpose. Okay. So the eigenvalues of a symmetric matrix will all be real numbers, no imaginaries. Number 2, the eigenvectors of a again, all these statements, notice, are about symmetric matrices. The eigenvectors of a symmetric matrix A that correspond to distinct eigenvalues or different eigenvalues will be orthogonal. Right, so if you so for instance, say a symmetric matrix has eigenvalues of 2 and 3. Well, then any eigenvector corresponding to 2 will be orthogonal to any eigenvector corresponding to 3. So any pairs of eigenvectors corresponding to different eigenvalues of a symmetric matrix will be orthogonal. Again, this is only for symmetric matrices. And we'll see this when we get to our examples as well. All right, and then I think here's the most important part, put little stars around it, different colors. Number 3. Here's the condition under which, the only condition that you need to verify to determine whether or not a matrix is orthogonally diagonalizable. If you can, to determine if you can find an orthogonal matrix P such that P transpose times A times P equals a diagonal matrix. So a matrix A is orthogonally diagonalizable if and only if, right? This goes in both directions, so these are equivalent statements. If and only if A is symmetric. So if A is orthogonally diagonalizable, then it will be symmetric. If it is symmetric, then it will be orthogonally diagonalizable. Okay, and if it's not symmetric, it's not orthogonally diagonalizable. Right? I've given you right here the only condition you need to check for to state whether or not a matrix is orthogonally diagonalizable. Now you got to be careful. All right, don't confuse orthogonally diagonalizable with just diagonalizable. Right, there was a video, again, I put up in the past on just the diagonalization of a matrix. A matrix can be diagonalizable, but not orthogonally diagonalizable. Okay. Now, if you're orthogonally diagonalizable, then you're diagonalizable because you can find a matrix such that the inverse times A times P equals some diagonal. So every orthogonally diagonalizable matrix is diagonalizable. It's in the name. But not every diagonalizable matrix is orthogonally diagonalizable. All right, so please understand that those are different things. Okay. So one more page here before we get into some examples. Just going to describe the procedure. How do we find this orthogonal matrix P such that P transpose times A times P equals a diagonal matrix. So here it is here. So the steps to orthogonally diagonalize a symmetric matrix A. Number 1. Find a basis for each eigenspace of A. So this is easier said than done here. This is going to take a while. Because remember, you have to find the eigenvalues of A. So you're solving that characteristic equation first, and then you take each eigenvalue and find a basis for the eigenspace of each eigenvalue of A. So that takes a bit, but it can be done. Number 2, apply the Gram-Schmidt process if necessary. All right, it may not be necessary, but apply that Gram-Schmidt process to get an orthonormal basis for each eigenspace. All right, so you'll have a basis for each eigenspace, but then you're going to make sure that each of those bases is an orthonormal set. All right, that you have an orthogonal set of vectors where each vector is a unit vector. And again, I'm just going to go under the dot product. All right. And then once you have every basis, right, once every basis of every eigenspace is an orthonormal set of vectors, then we can use those vectors, those orthonormal sets of vectors, to form that matrix P. Matrix P will be formed using those orthonormal basis vectors as columns. And you'll have constructed an orthogonal matrix P such that P transpose times A times P will be equal to a diagonal matrix D. And what you're going to notice, just like back with regular diagonalization, that diagonal matrix D will have down its main diagonal the eigenvalues of A, in the same order that you put these orthonormal basis vectors. All right, and again, we're going to see that in our examples. Okay, so once more through, and I'll do the same. I'll do the steps in some examples. So you find each eigenvalue and a basis for each eigenspace of A. Set it up, transform each basis, transform each eigenbasis into an orthonormal basis for those eigenspaces. And then using those orthonormal basis vectors as columns, you construct matrix P. And then you'll have a matrix P that orthogonally diagonalizes matrix A. Okay. So now the rest of the video is just me doing this. Okay. Performing these steps, performing this procedure to orthogonally diagonalize a symmetric matrix. Well, first I want to determine whether or not the matrix is diagonalizable. So, my instructions for the rest of the video, every example for the rest of the video, I have determined whether the matrix A is orthogonally diagonalizable. And if you recall from earlier, that spectral theorem, this is the same thing as asking to determine whether the matrix is symmetric. Because the matrix will be orthogonally diagonalizable if and only if it is symmetric, if it's equal to its own transpose. If it is symmetric, if it is orthogonally diagonalizable, then find a matrix P, right, an orthogonal matrix P that orthogonally diagonalizes A, right? So that such that P transpose times A times P equals D, where D is diagonal. All right, so my first example is a 2 by 2 matrix. All right, 2 by 2 matrix. A equals, in the first row is 4, 5. The second row is 0, 1. What is A transpose? All right, first I'm trying to determine whether or not this is orthogonally diagonalizable. Remember, the transpose is simple, right? The first row of A, row and column numbers switch, right? The first row of A becomes the first column of A transpose, and the second row of A becomes the second column of A transpose. And notice that these are not the same matrix, right? These do not have, the first row, second column entries aren't the same. The second row, first column entries are not the same. Right, so these are not equal. Matrix A is not equal to matrix A transpose. That means that A is not symmetric. Is not symmetric. Therefore, A is not orthogonally diagonalizable. Okay, and I'm done with this problem. Now, as I said earlier, just because a matrix isn't symmetric, right, just because a matrix isn't orthogonally diagonalizable, doesn't mean it's not diagonalizable. Right? If you recall here, this is what they call A is an upper triangular matrix, right? The only non-zero entries are above the main diagonal, and everything below the main diagonal is 0. So remember the spectrum of A. Remember the spectrum of A is the set of all the eigenvalues. Would be the diagonal entries, right? It would have eigenvalues of 4 and 1. So it's a 2 by 2 matrix with 2 distinct eigenvalues. So you can tell me from right there that A is diagonalizable. It would be diagonalizable. But it is not orthogonally diagonalizable. Okay, so a matrix can be diagonalizable without being orthogonally diagonalizable. Right, just be careful, right, and understand that these actually are different concepts. Right, they're very similar, but they are different. And I'll say it one more time. Every orthogonally diagonalizable matrix is also diagonalizable. Right? It's in the name. But not every diagonalizable matrix is orthogonally diagonalizable, as we're seeing here. Right? This is diagonalizable, but it's not orthogonally diagonalizable because it's not symmetric. It's got to be symmetric to be orthogonally diagonalizable. Okay, so easy one to start with. Right? Here's a matrix that wasn't symmetric, so not orthogonally diagonalizable. Okay. My next example, another 2 by 2 matrix. Notice that this matrix is symmetric. If you were to do A transpose, right? The first row is 4, 2. Well, so is the first column. The second row is 2, 4. So is the second column going down 2, 4. This is a symmetric matrix. Right? So A is symmetric. It's equal to its own transpose. Therefore, this matrix is orthogonally diagonalizable. And again, it's that simple to check if your matrix is orthogonally diagonalizable. All right. So what does that mean? Right. this means that we can find an orthogonal matrix P, basically writing the definition again for you. I'm not going to do this for every example, but we can find an orthogonal matrix P, right? A matrix where, the columns form an orthonormal set. We can find an orthogonal matrix P such that P transpose, which would be P inverse, right? It's orthogonal, times A times P is equal to a diagonal matrix D, right? Okay, so remember those steps. So, step 1. I'm going to find a basis for each eigenspace of A. Alright, so again, I said earlier, this entails a lot. Alright. First, I'm going to break this up into like sub-steps. First I would have to find the eigenvalues of A. Alright, so this is part of the first step. So part there. Right, so find the eigenvalues of A. So recall how to do that. That you're solving that characteristic equation. That when is the determinant of A minus lambda times the identity matrix A minus lambda I. When is that determinant equal to 0? Or when is A minus lambda I a singular matrix, non-invertible matrix? Alright, so let's go back up to what A looks like. Right? And A minus lambda I, the determinant is this. The bar symbol for a determinant. Remember, when you do A minus lambda I, that's just subtracting lambda down the main diagonal. So we got 4 minus lambda, 4 minus lambda, down the main diagonal, and then all the other entries remain the same. And what is this determinant? Right? This is 4 minus lambda times 4 minus lambda again. This is a 2 by 2, and then minus 4, minus 2 times 2. Well, what I have here is a difference of squares. Right? This is 4 minus lambda squared minus 2 squared. So I can factor this to 4 minus lambda minus 2 times 4 minus lambda plus 2. And if I simplify these, this would be 2 minus lambda multiplied by 6 minus lambda. And the question is, now I have a fully nice, completely factored polynomial here. This is the characteristic polynomial, completely factored. And the question is, when is this equal to 0? Right? And this equals 0 when lambda is 2. Right? When lambda equals 2, or when lambda equals 6. So hopefully that looked all familiar to you, right? Finding the eigenvalues of a matrix. Right, so the spectrum of matrix A here, the set of all the eigenvalues is 2 and 6. And notice that those are both real numbers, right? Remember that spectral theorem earlier, one of the statements was a symmetric matrix will have eigenvalues that are all real. Right, no imaginaries, and that is happening here. Alright, so that's finding the eigenvalues of A, and then I need to find the the eigenspaces, right, the eigenvectors corresponding to these eigenvalues. Right. So the second part of the first step. So let's find the eigenspaces. Corresponding to each eigenvalue. Alright, so I'll start with lambda equals 2. And remember, the eigenspace corresponding to a particular eigenvalue was just the null space of A minus lambda I. So that means we're solving this matrix equation here. You know, A minus 2I, right? Lambda's 2 times, you know, some vectors x. When is this equal to the 0 vector? Right? I'm finding the null space of A minus 2I, and that'll be the eigenspace corresponding to lambda equals 2. Alright, so again, just here's matrix. There's A minus lambda I here, right? Just replace lambda with 2, and we've got this equation. Right? The matrix, again, this isn't determinant now, it's just the matrix, so little brackets. A minus 2I, well, if I replace lambda with 2, we're getting matrix with all 2's. You know, times my variable vector x here would just have 2 components, say x1 and x2. And then the other side is the 0 vector, right? The two-dimensional 0 vector. And then I could make an augmented matrix here where I have, you know, 2, 2, 2, 2, little bar, and then 0, 0, and put this into reduced echelon form or reduced row echelon form, which would be pretty simple to do by hand here. I'm not going to go to the calculator or anything, because you see that the first row and second row are the same. So I would just multiply the first row by -1, add it to the second row. That would make the second row all zeros. Right, so I'd have 0, 0, little bar for the equal sign, 0, and then the first row, to get it, you know, I want the lead non-zero entry, the pivot entry, to be a 1 in reduced row echelon form. So I multiply the top row by a half, get 1 and 1, and then again there's still zeros. Any column of zeros is going to stay a column of zeros. So here we are in reduced echelon form. You know, look at my pivot columns. The only one is the first column here. So x1 is a leading variable or a basic variable, and x2 is free. So I'm going to let x2 be t, where t is any real number. And then from the first row, you know, we're seeing that x1 plus t must be 0, so x1 must be, you know, the opposite of t. So the solutions to this equation, a minus 2I times x equals 0, are the following. X can be replaced by any, you know, there's only one free variable, t, here, and, you know, x1 is -1 times t, x2 is 1 times t, so this is t times the vector -1, 1. So there's an eigenvector corresponding to lambda equals 2. There's a -1, 1. But I can use this to write my little, you know, the Eigenspace corresponding to lambda equals 2. Right, again, it's just the null space of A minus 2I. So the Eigenspace, remember that was a E with a subscript of 2 of matrix A, right? The Eigenspace of A corresponding to lambda equals 2 is just the span, right? Every single solution to this equation is just a scalar multiple of the vector -1, 1. Is the span of the set with the vector -1, 1. Alright, so I have a basis for this space. A basis for this space is the set with the vector -1, 1, clearly. Alright, so that's one basis. Right, one of the bases. That was just the one corresponding to lambda equals 2. Alright, I'm going to do the same thing. Right, find the eigenspace now corresponding to lambda equals 6. Alright, right? So for lambda equals 6, same stuff. Right? So for lambda equals 6, we are solving this equation, right, to find the eigenspace of A corresponding to lambda equals 6. That's finding the null space of A minus 6i. So A minus 6i, right, times some vector x, when's this equal to the 0 vector, right? All right, so what is, A minus 6i? Just replace lambda. There's A minus lambda I here. Replace lambda with 6, and it's not the determinant, right? So I'm not using straight bars, just the brackets. So we'll have negative 2, 2, and then 2, negative 2, times, some vector with two components, say x1 and x2 again. And this is equal to the 0 vector, right, from R2. Alright, and then as before, I can put the system here as an augmented matrix into reduced row echelon form. Again, only a couple rows here. Don't need to go to a calculator. This is pretty simple. If I just add the first row and the second row is full of zeros. A little equal sign bar there. And then the first row, to get it, the pivot position, the leading non-zero entry to be a 1, I multiply everything by negative 1/2. So if you make this positive 1, then times negative 1/2, make that negative 1, and again 0 over the other side. Alright, and then just like last with the lambda equals 2, the first column is a pivot column, so x1 is a basic or leading variable. Then this is not a pivot column, right? So x2 is free. And you know me, I like to replace my free variables with other parameters, other expressions that represent real numbers. So I'm going to have x2 be t, where t is any real number. And then from the first row, we're getting that x1 minus t minus x2 minus t equals 0. So x1 must also be equal to t. Alright, so I can state what the Eigenspace is right now. Right? Every solution of this equation is some multiple of the vector 1, 1. Right? This is t times 1, t times 1. Right? So a multiple of the vector 1, 1. So the Eigenspace of A corresponding to lambda equals 6 is just the span of the set with the vector 1, 1 in it. Okay, and we have a basis then. Right? It's very obvious then that a basis for this eigenspace is the set with the vector 1, 1. Right. And that was it for that. Right? Now I'm done with step 1. Sorry, but that basis is the set with the vector 1, 1. So I found a basis for the eigenspace corresponding to lambda equals 2, the set with the vector negative 1, 1, and a basis when lambda equals 6. Now, one other thing to point out. Remember that spectral theorem from earlier in the video. One of the statements was that pairs of eigenvectors for distinct eigenvalues will be orthogonal. Another way to say that is that the eigenspaces corresponding to distinct eigenvalues, to different eigenvalues, will be orthogonal subspaces, will be orthogonal vector spaces. So if you take any vector in the eigenspace corresponding to 2, and then any vector in the eigenspace corresponding to 6, those vectors will be orthogonal, and you can tell by looking at the basis vectors. Now there's only one basis vector here, so there's only one. You just do the dot product of these two. What's the dot product of negative 1, 1 with 1, 1? That would be 0, wouldn't it? So that tells me that the eigenspace corresponding to 2 is orthogonal to the eigenspace corresponding to 6. Right? If you took any multiple of negative 1, 1 and did the dot product with any multiple of the vector 1, 1, you're going to get 0. Right? And this was from the this was something that was stated in that spectral theorem. Right? That basically the eigenspaces corresponding to different eigenvalues will be orthogonal spaces. Every vector in one and every vector in the other will be orthogonal. Alright, so that was step 1. Right, finding a basis for each eigenspace of matrix A. Alright, and then part 2 is to transform these bases into orthonormal sets using Graham-Schmidt if necessary. Right, so step 2 was, I'll just say, transform each eigenbasis into an orthonormal set, into an orthonormal basis. Now this example's nice, right? An orthonormal set, orthonormal basis. This example's nice. Now I'll write the bases again. Right, so here were our eigenbases. We had the basis corresponding to lambda equals 2 was, the set with the vector negative 1, 1. And the basis corresponding to when lambda was equal to 6, that was the set with the vector 1, 1. Okay, so now the thing is, make these into orthonormal sets. So this one's it's a nice example because each basis only has a single vector. All right, so I don't need to go through and do, Graham-Schmidt to these bases. That was really when you had a set of more than one vector that wasn't orthogonal. You could use the Graham-Schmidt process to transform it into orthogonal and then normalize each vector, right? Divide each vector by its norm to get an orthonormal set. Alright, so I'll start off with, this basis here, right? The basis for when lambda was equal to 2. You could say it was orthogonal, this set, because it's only got one vector, right? But it's not orthonormal. Right, what's the norm of this vector? Right, so I'm going to call these vectors some names. So let's call this, say, vector v1. And over here, when we look at this set, vector v2. Right? But again, right now I'm working on just the first basis. So I'm going to, there's only a single vector. So all I need to do is normalize that vector. No need for the Graham-Schmidt process here. So what's the norm of v1? What's the norm of this vector negative 1, 1? Remember, the norm was the square root of the inner product of the vector with itself. So that's the square root of, and the inner product here is the dot product. The dot product of negative 1, 1 with itself would be, negative 1 squared, 1 plus 1 squared, 1, that's 2. Square root of 2. So I just need to divide each of these components by the square root of 2. So here's an orthonormal basis for that eigenspace when lambda equals 2 is this vector here. Negative 1 over the square root of 2 and then 1 over the square root of 2, right? Just dividing the vector by its norm. There. Now I have a unit vector. Right. And what I'm going to do is I'm going to make this vector the first column of that matrix P, that orthogonal matrix P that we're going to make. Same thing here. All right, now I'm done with that basis. I look at this basis now, the basis for when lambda was equal to 6, and I do the same thing. Now again, this only has a single vector in it, just the vector 1, 1. So there's no need for like the Gram-Schmidt process. I just simply need to make sure that this is a unit vector. So again, I normalize this vector. What is the norm of vector 1, 1, that vector I called v2? That would also be the square root of 2. All right. So here, dividing that single vector by its norm, here is an orthonormal basis for the eigenspace when lambda was equal to 6. All right, it would be the set with the vector, 1 divided by the square root of 2, 1 divided by the square root of 2. And if you want to rationalize these, you can, make them into square root of 2 over 2. But I'll leave them this way, which is totally fine. And I'm going to make this orthonormal vector, basis vector. This is going to be the second column of my matrix P. All right. So there, I'm done with step 2. I've taken each eigenbasis and constructed from it an orthonormal eigenbasis. So you do it for each of them. And again, there was only a single vector in each, so I didn't really need, the Gram-Schmidt process. I just needed to normalize that vector, make it into a unit vector. All right, then finally, part 3, we get our matrix P. Right. So construct matrix P using the orthonormal basis vectors as columns. So the matrix P that orthogonally diagonalizes A is this. So P equals a 2 by 2 matrix where down the first column I'll put this -1 over the square root of 2 and 1 over the square root of 2, right? This orthonormal basis vector, when lambda was 2. And the second column, this orthonormal basis vector when lambda was 6. 1 over the square root of 2, 1 over the square root of 2. All right, and do you see how the columns form an orthonormal set? This is an orthogonal matrix. And it will be if you did everything prior to that correctly. You will have an orthogonal matrix. Meaning that, P transpose is equal to P inverse. Right? And you can verify this. All right, verify this. Multiply P by its transpose and see that you get the identity matrix. All right. All right. Now let's see that P. Let's see that that P diagonalizes A. So there was P. All right, P transpose would be this matrix, and the P transpose should be its inverse, right? So that's -1 over the square root of 2. 1 over this. This is also symmetric. That's not always going to happen. 1 over the square root of 2. Okay, and then let's check. Let's find P transpose times A times P and see what we get. Now, if you did everything correctly, and I'm pretty sure I did, this should be equal to a diagonal matrix. And it's a diagonal matrix where down the main diagonal I'll have the eigenvalues of A in the same order that I put these columns of P. Right? Now remember the first column of P came from a basis corresponding to lambda equals 2. And the second column of P came from a basis corresponding to lambda equals 6. So when I'm done with this, I should get this matrix 2 and 6 down the main diagonal, right? The eigenvalues in the same order that I put the columns of P, and then 0 everywhere else, right? It's a diagonal matrix. There was the D. All right. And again, let me verify this. All right. So I'm going to go to the calculator and enter these matrices. All right. So second matrix over to edit. So I'm going to take some time here. I'll pause it and be right back after I've entered these matrices, and we'll see these products. Okay, so I'm back, and I entered matrix A was a 2. I know the matrix A was actually P, all right, and matrix B was A, all right, in my calculator. So remember, A was that matrix way back here with the 4, 2, 2, 4. So I called this was matrix. I should have made this matrix A, but this is matrix B in my calculator. And then matrix P, I set up. This is matrix A in my calculator. So I have A transpose B A. Right, see off here. See A transpose B A, and look at the final result. 2006, as we expected. Right, and then again down the main diagonal are the eigenvalues of A in the order that the columns of P come in. Right, so again down the main diagonal, these are the eigenvalues of A. Wonderful. So we can say, finally, we can say that this matrix, right, the way that what we would say then is that this matrix, we would say that P orthogonally, because it is an orthogonal matrix, right, P orthogonally diagonalizes A into D, right, into D. Right. But the key word being orthogonally, telling me that P is an orthogonal matrix, right? Its transpose is its inverse. Great. All right, and that's, you can see from this for this first example with a 2x2 symmetric matrix. This can take a while. All right. So in my next examples, I'm going to be doing a little more pausing and skipping ahead, where I'll state a step. It's the finding of the eigenvalues and eigenbases that probably take the longest. So I'm going to kind of skip over those and just show you what they'll be. And I hope you have seen enough and remember from earlier videos how to find the eigenvalues of a matrix, and also the corresponding eigenspaces. All right, so I'm going to stop doing that in this video and just skip ahead to the construction of the matrix P. All right, so that was a 2x2. My next example is my next example is a 3x3. So 3x3 matrix. Now the first question was, the first instruction was, determine if the matrix is orthogonally diagonalizable. Well, again, this matrix is symmetric. Notice if I wrote the first row is the first column, the second row is the second column, the third row is the third column. So A is symmetric. A is orthogonally diagonalizable. Alright, so since it's orthogonally diagonalizable, again, the first step is to find a basis for each eigenspace. Right, so I'm going to pause here and write out the steps, and I'll slowly scroll them up for you so you can maybe pause the video yourself and try to verify that my calculations are correct and all that, and maybe even write it out as you want. But I would suggest you try finding it yourself as well. So let's find a basis for each eigenspace. Okay, so I'll be right back. It'll look like a flash because I'm just pausing it here, and show you the calculations. Okay, so I've gone through and found the eigenvalues and corresponding eigenbases for the eigenspaces corresponding to the eigenvalues. Alright, so I've written out the calculations here. Again, hopefully you've done this on your own. You can do it on your own. But just to check me, I might want to go through this. Alright, so finding the eigenvalues, I was solving the characteristic equation. Alright, the determinant, when is the determinant of a minus lambda I equal to 0? Here's a minus lambda I. I did cofactor expansion down the third column, or the third row, since it's symmetric, you could say this. So here it is here, and then I expanded, got down to eventually the polynomial negative lambda cubed plus 225 lambda, which factors to negative lambda times lambda minus 15 times lambda plus 15. So the eigenvalues, right, the spectrum of A, has the values 0, negative 15, and positive 15. All right. So I'll keep this up here. You can pause it, look over it, write it out if you wish. All right, then for lambda equals 0, I found the eigenspace. Right, for lambda equals 0, I was solving a minus 0I, or just a, times x equals the 0 vector. Put a in reduced row echelon form, got this. X3 was a free variable. I let it be 2t because of the fraction there with the half. And if I let x3 be 2t, for t being any real number, then x2 would be negative 2t, and x1 would have to be t. So the eigenspace of A corresponding to 0 will be the span of the vector 1, negative 2, 2. Right. Then for lambda equals negative 15, and I'm solving a minus negative 15i or a plus 15i times x equals 0. You just add 15 to the main diagonal entries of A, add 15 to the main diagonal entries of A, and then I put that in reduced echelon form with my calculator real quick. And again, I let x3 be 2t because of the half there, right? And then x2 would be t, x1 would be negative 2t, where t is any real number. So then the eigenspace of A corresponding to negative 15 is the span of the vector negative 2, 1, 2. Which you'll notice that negative 2, 1, 2 would be orthogonal with 1, negative 2, 2 under the dot product, right? If you took the dot product of these two basis vectors, you'd get 0. As it should be for a symmetric matrix. Remember, the eigenspaces of symmetric matrix of the different eigenvalues of a symmetric matrix should be orthogonal. All right, then for lambda equals positive 15, I'm solving a minus 15i times x equals 0. Just subtract 15 from the main diagonal entries of A. I put it in reduced row echelon form. Let x3 be t, for t is any real number. And then both x1 and x2 would be 2t. So the eigenspace of A corresponding to 15 is the span of the vector 2, 2, 1. All right, and I've written out the bases for each of these. All right. So there we go. There's step 1. All right. Find a basis for each eigenspace. The basis for the eigenspace corresponding to lambda equals 0 is the set with the vector 1, negative 2, 2. When lambda was negative 15, it had the set with the negative 2, 1, 2. And when lambda was 15, the set with 2, 2, 1. And again, you can take any pair of these. These two, the second and third, the first and third, take the dot product of any pair of these and you'll get 0. These are orthogonal vectors. But they don't form an orthonormal set. All three of these together do form an orthogonal set, but not an orthonormal set, right? And we're trying to make an orthogonal matrix, and we need the columns to be an orthonormal set. So again, no need for Graham-Schmidt. I have one more example after this where I will use Graham-Schmidt, but there's only a single vector in each basis again, right? So just like last example, since there's only a single vector, I only need to normalize each vector to get orthogonal bases. Orthonormal bases. So here are the orthonormal bases for the eigenspaces. When lambda was equal to 0, we have the set with. Now the norm of this vector. Right, remember the norm of a vector is the square root of the dot product or the inner product with itself. The dot product of this vector with itself would be 1 plus 4 plus 4. That's 9, and then the square root of that. The norm of actually each of these vectors is 3. So I'm going to divide that vector by 3, that vector by 3, that vector by 3. So we're getting from when lambda was 0, 1/3, negative 2/3, 2/3. We're just dividing that vector by its norm. When lambda was negative 15, again, only a single vector, so all I need to do is normalize, divide by its norm. Again, the norm would be 3, the square root of 9, right? So an orthonormal basis, a unit vector basis for the eigenspace corresponding to lambda equals negative 15 would be the vector negative 2/3, 1/3, 2/3. Alright, and then finally, for when lambda was 15, our basis, again, just a single vector, so just normalize it. Again, the norm is square root of 9 again, right, just 3. So I divide each component by 3, 2/3, 2/3, 1/3. Right. Okay, so now we can construct P, right? So the matrix P that we construct will be an orthogonal matrix, meaning each, the set of all the columns form an orthonormal set. Here's the first column, right, 1/3, negative 2/3, and 2/3. Second column from this, orthonormal basis for the eigenspace when lambda was negative 15, you have negative 2/3, 1/3, and 2/3. And then the last column for when lambda was 15, I forgot to close that off, 2/3, 2/3, 1/3. Okay. This, if I did everything correctly, should orthogonally diagonalize matrix A. Alright, now I'll leave it to you to verify this time. Okay, so copy this down, this matrix P I just created. And you can verify that it's an orthogonal matrix by multiplying by its transpose. Multiply this matrix by its transpose and see if you get the identity matrix back, right? The transpose should be its inverse. And then to verify that it orthogonally diagonalizes A, again, I'll leave this to you. But you should verify the following, right? You should verify that the matrix I've created here, if you take P transpose times A, right, so times that that matrix from the beginning of the problem. All right, there's A with 0, 10, 10, 10, 5, 0, 10, 0, negative 5. Verify that P transpose times A times P is equal to a diagonal matrix, and it'll be a 3 by 3 diagonal matrix where down the main diagonal are the eigenvalues of A in the order that I put these orthonormal columns. So the first one came from the orthonormal basis for the eigenspace when lambda was 0. So 0 first down the main diagonal. And then the second column came when when lambda was negative 15. The third column came from when lambda was positive 15. So I have that down the main diagonal and 0 everywhere else. Okay. And this is that matrix D that was being talked about. You can verify this, right? Do it yourself. Punch this matrix in your calculator, the original matrix A in your calculator, and then do this transpose times A times this, and see if you should get this matrix back, right? This diagonal matrix with 0, negative 15, and positive 15 down the main diagonal. Right. And if you were to switch the order of the columns here, if you say switch the first and second column, all that would do is switch the first and second eigenvalue down the main diagonal, right? If you just switch the order of the columns, it'll just switch the order that the eigenvalues come in down the main diagonal. Okay, all right, so there was a 3 by 3. Now, so far, in my 2 by 2 example, and my 3 by 3 example, every single basis, every single eigenbasis, had one vector in it. So to make those unit vectors, I just had to normalize, right? We didn't have to use the Graham-Schmidt process at any point. Well, my final example, I'm going to have an eigenbasis with more than one vector, so we'll have to apply the Graham-Schmidt process to make an orthonormal set. All right. So my last example, pardon me, another 3 by 3. It is symmetric. Pardon me. All right, the first row is the first column, the second row is the second column, the third row is the third column, right? This is a matrix that's equal to its own transpose. So the matrix is orthogonally diagonalizable, right? It's if and only if it's symmetric. Great. So now let's do it. Let's find that matrix P, that orthogonal matrix P, such that P transpose times A times P is a diagonal matrix where, the entries down the main diagonal are the eigenvalues of A. Alright, so just like last example, I'm going to pause it here. It'll look like I'm coming back in a flash, but I'm going to have a bunch of calculations written out where I find the eigenvalues and the eigenspaces corresponding to those eigenvalues, and also the bases. Alright, so I'll be back in a flash. Okay, and we're back. So I can hope you tried this on your own too, but so first I want to find the eigenvalues, solving the characteristic equation. When is the determinant of A minus lambda I equal to 0? There's the determinant of A minus lambda I, right, just subtracting lambda down the main diagonal. I just did cofactor expansion down the first row, and I'll keep this. You can see that, pause it if you want to write it down, follow along. And I eventually got down to this polynomial here, which was negative 1 times lambda minus 2 squared times lambda minus 5. And when does that equal 0? Well, when lambda equals 2 or when lambda equals 5. Alright, so lambda equals 2, lambda equals 5. That's the spectrum of A, right? The set of all the eigenvalues of A. 2 has an algebraic multiplicity of 2 this time, though. Right? And 5 has an algebraic multiplicity of 1. Alright, and then when lambda was equal to 2, I want to find the eigenspace. Alright, so we're solving a minus 2i times x equals the 0 vector. Just subtract 2 down the main diagonal of a. I put that in reduced row echelon form. It's just a bunch of 1s here. So you see there are 2 non-pivot columns, 2 free variables. So I let x2 be s and let x3 be t, where s and t are real. And then from the first row, we're seeing that x1 would be negative s minus t. Alright, so the eigenspace of A corresponding to lambda equals 2 is the span of 2 vectors, right? One for each free variable. The first vector has the coefficients of s, negative 1, 1, and 0, down x1, x2, x3. And the second vector in the basis for this space has the coefficients of t, negative 1, 0, 1. Right? So the eigenspace of A corresponding to lambda equals 2 is the span of negative 1, 1, 0 and negative 1, 0, 1. Alright, then for lambda equals 5, for lambda equals 5, I was solving, a minus 5i times x equals 0. Just subtract 5 from all the diagonal entries of A, put it in reduced row echelon form. There was only one free variable this time, so I just called it t. And each variable would have been equal to t. So the eigenspace of A corresponding to lambda equals 5 is just the span of the vector 1, 1, 1. Alright, so I've got my bases. Right. Here were the bases for the eigenspaces of A. Right. Now the basis when lambda was equal to 5 is just the set with the vector 1, 1, 1. Just a single vector. So I can normalize that just like I did in the last examples. It's this other basis that's the problem. Right. So my basis when lambda was equal to 2 had the vectors negative 1, 1, 0 and negative 1, 0, 1. This is not an orthonormal set. It's not even orthogonal. Right? It's not even an orthogonal set. If you took the dot product of negative 1, 1, 0 and negative 1, 0, 1, you're going to get 1, not 0. Right? These aren't even orthogonal vectors. So here's where the Graham-Schmidt process comes in. And I've done this in several videos before. Hopefully you're familiar with it. Right? The Graham-Schmidt process to make this, use this basis for this eigenspace and transform it into an orthogonal basis for the eigenspace, and then we can normalize the vectors, make them unit vectors to make it an orthonormal set. So I'm going to call this first vector, say u1, and this vector, say u2. All right. The negative 1, 1, 0 is u1, negative 1, 0, 1 is u2. So Graham-Schmidt, what I'm doing is I'm going to construct first an orthogonal basis for this eigenspace. Say it has the vectors, say, v1 and v2. Alright, so v1 is simply, in this orthogonal basis, is simply the first vector from your original basis. So v1 equals u1. So it's just the vector negative 1, 1, 0. Okay? Then the second vector in the orthogonal basis is the second vector from the original basis, but then you subtract the projections of that second vector onto all the earlier vectors in the orthogonal basis. So there's only one previous vector, so I subtract the projection of vector u2 onto vector v1, right, onto the earlier vectors in my orthogonal basis. All right, so what is this, right? u2 is the vector negative 1, 0, 1 minus, and remember how projections go. Remember, it's the inner product of these two vectors in the numerator divided by the inner product of the vector you're projecting onto with itself in the denominator for the scalar, and then times that vector you're projecting onto. So what is the dot product of v1 and u2? Well, that's just I said it earlier, it was 1. right? So the numerator is 1 of this for the scalar. The denominator is the dot product of v1 with itself, which would be 2, right? v1 with itself would be 1 plus 0 times vector v1, right, times negative 1, 1, 0. And putting these together, we're getting our second vector in this orthogonal basis is negative 1, plus a half, right, because you have minus a half times negative 1. Negative 1 plus 1 half, that'd be negative 1 half. 0 minus a half, negative 1 half. And 1 minus a half, which would be positive 1 half. Which, if you'd like, I can call this is a half times the vector negative 1, 1, if you want to write it that way as well. Alright, so these two vectors now form an orthogonal set. And let's double check. Take the dot product of v1 and v2. It would be a positive half minus a half plus 0. That is 0. These are orthogonal vectors. But they don't form an orthonormal set yet. Alright, now I just construct an orthonormal basis by normalizing these two vectors. Alright, so then I just normalize. Alright, so what's the norm of the first vector? Well, that'd be the square root of 2. Right? Remember I said the dot product of this with itself was 2, and you take the square root of the inner product with itself, so the square root of 2. And what's the norm of vector 2? Well, remember that's the only reason I pulled this scalar out is because it's going to, the norm of this vector, it's going to be the norm of the vector negative 1, 1, but cut in half. Remember when you multiply a vector by a scalar, it cuts the norm, the length of it by that scalar. So the norm of this vector is the square root of 3, right? 1 plus 1 plus 1 is the dot product with itself. And then the square root, the norm of this vector is the square root of 3, but that's cut in half, right? So it's equal to the square root of 3 over 2. Right? Or since I'm going to be multiplying or dividing by the reciprocal, I'm going to be multiplying by the reciprocal of these things. I'll just actually leave these the way they are. So the normalized vectors. So here I'm going to have, here's my orthonormal basis. Here's the orthonormal basis. Take vector v1, divide it by its norm. So I've got the vector with negative 1 over the square root of 2, 1 over the square root of 2, and 0. All right, that was vector v1 divided by its norm. All right. And then the second vector in the orthonormal basis for this eigenspace corresponding to lambda equals 2 is my vector v2. Again, divided by its norm. Now, I'm not going to divide by a fraction. Right? Dividing by the square root of 3 over 2 is the same thing as multiplying by 2 over the square root of 3. Right, so I'm going to take this vector here, multiply by 2 over the square root of 3. Well, that'll cancel all the 2's and put square roots of 3's in the denominator. So it'll be negative 1 over the square root of 3, negative 1 over the square root of 3, and 1 over the square root of 3. And if you want to rationalize these, go ahead, right? But I'll leave it the way this is with the square roots in the denominator. And this is fine. Now I have an orthonormal set. Right? The dot product of these two is 0, and they're both unit vectors now. Right? So these are going to be some columns in that matrix P that I'm going to make. All right, and so that was for when lambda was 2. Right, and then the only other eigenvalue was when lambda was 5. Right, that was this. When the basis for the eigenspace when lambda was 5 is 1, 1, 1, the vector 1, 1, 1. The norm of this vector under the dot product, right, would be the square root of 3 again. So I'm just going to divide this by the square root of 3, and we get our orthonormal. Again, I use the orthonormal loosely here with just a single vector, but we get a basis with a unit vector, right? Our orthonormal basis for the eigenspace is the vector 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. Alright, so these three will be the columns of that matrix P that orthogonally diagonalizes matrix A. So let's write it. So here it is, matrix P equals a 3 by 3 matrix, where I'll make these two the first two columns. Right, so negative 1 over the square root of 2, 1 over the square root of 2, 0. The second column, negative 1 over the square root of 3, right, just using these orthonormal basis vectors, negative 1 over the square root of 3, and 1 over the square root of 3, and finally 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. All right. Okay, and yeah, this should be good. This is an orthonormal set of vectors here. Right, you can take the dot product of any pair of them. Right, take the dot product of these two, and you get 0. Take the dot product of the first and the third, you get 0. Take the dot product of the second and the third, you get 0. No, that's not true. Hold on, I gotta fix something. Something's gotta be fixed. I apologize. Okay, my deepest apologies again. I'd noticed going back, because I was like, hey, these two vectors are not orthogonal, but they should be, right? You might have noticed that. So this is actually pretty bad. All right, this isn't good. The first one's fine. It's these two that are wrong. All right, blacken them out here. All right. Where my mistake was in the Graham-Schmidt process, and you may have caught it. Remember when I was constructing V2, I took U2 negative 1, 0, 1 minus 1/2. This was the dot product of U2 and V1 divided by the dot product of V1 and V1 times V1, and I got negative 1 plus 1/2 is negative 1/2, 0 minus 1/2 is negative 1/2, and then 1 minus 0. I did 1 minus 1/2 for some reason. This should be 1 down here. So when I pull a 1/2 out, this component is 2. So it's half of negative 1, 1, 2, not half of negative 1, 1, 1. And that changes this right here. So again, my apologies. The norm of V2 would be half of the norm of this vector, which would be 1 plus 1 plus 4. That's the square root of 6. So it would be the square root of 6 cut in half, not the square root of 3. Right, and then multiplying by the reciprocal of this gets rid of the 2's and puts all these over the square root of 6. Alright, so my orthonormal basis would be V1. V1 again is negative 1, 1, 0, so divide that by the square root of 2, normalize it. And then V2 is this vector now, negative 1/2, negative 1/2, 1. My apologies. So again, multiplying this by 2 over the square root of 6, right, gets rid of the fraction 1/2 and puts all these over the square root of 6. So negative 1 over the square root of 6, negative 1 over the square root of 6, and 2 over the square root of 6. Alright, so let me reconstruct matrix P here. Again, see how a simple arithmetic error. You pass it up too fast and it throws everything off. Now I did catch it at the end because I noticed, hey, these aren't orthogonal vectors in my columns. So I'm hoping you catch mistakes like that as well. But you see how a simple arithmetic error can throw everything off. Alright, so now using these as columns, here are my orthonormal basis vectors. These were the orthonormal basis vectors when lambda was 2. right? Lambda was equal to 2. And this was my orthonormal basis vector, my unit basis vector when lambda was 5. All right, so now let's construct that matrix P that orthogonally diagonalizes matrix A. All right. So our matrix P then will be this matrix here. So again, I'm going to use these as columns. So down the first column, negative 1 over the square root of 2, 1 over the square root of 2, and 0, right, that was this vector. Then negative 1 over the square root of 6, right, negative 1 over the square root of 6, and 2 over the square root of 6. Much better. And then the last column from the other orthonormal basis here, 1 over the square root of 3, 1 over the square root of 3, and 1 over the square root of 3. All right. This is an orthogonal matrix. All three vectors are orthogonal. Take any pair of them, do the dot product. You're going to get 0 this time. All right, great. And they're all unit vectors as well. So this matrix P is an orthogonal matrix. It is, if you were to take the transpose, it would be its inverse. All right. So again, I apologize profusely for what happened earlier. Little arithmetic error. So here's matrix P, and this matrix orthogonally diagonalizes A, matrix A, meaning the following, and I'll leave it to you to verify. Punch these in a calculator and test this out, or do it by hand if you want. But this matrix P that I have written here orthogonally diagonalizes matrix A. All right. Now matrix A, that was way back here, was this matrix with the 3, 1, 1 first row, 1, 3, 1 second row, and 1, 1, 3. Punch this matrix in your calculator, this matrix in your calculator, or again you can do it by hand. And to see that this matrix orthogonally diagonalizes this matrix, you need to verify that the following is true. That P transpose, right? Now notice here, this P is not symmetric, right? For my last couple of examples, the P was a symmetric matrix. That is not, like I said, it's not always happening. But P transpose times A, so this transpose times A times P, so times this matrix here, should be equal to, right, a 3 by 3 diagonal matrix. And the entries down the main diagonal will be the eigenvalues of A corresponding to these columns. Remember, the first two columns came from that eigenbasis for the eigenspace corresponding to lambda equals 2. So I'd have 2, then 2, and then this last column came from the eigenbasis corresponding to lambda equals 5. So 2, 2, 5 down the main diagonal, 0 everywhere else. And this is that matrix D that was mentioned earlier. All right. Okay, again, sorry for the little snafu with the arithmetic error when I was doing Gram-Schmidt, but the procedure is the same. Right? I didn't mess up on the procedure, and the way that P is constructed is the same. Nothing got messed up in any of that stuff. It was just the arithmetic. So there's a lesson for you, and I've done this in other videos where I've made mistakes and kept them in. One, the video is really long. I don't feel like going back and editing it or redoing stuff. And two, you learn from mistakes, right? You see, I hopefully you learn, as I have, to catch your mistakes too. Like, make sure you verify things at the end. If you were to take, if I took that P I put up earlier and did P transpose times A times P, you would see it wouldn't be this diagonal matrix, and you're like, ooh, what's wrong? And then go back and say, oh, wait a minute, hey, matrix P isn't even an orthogonal matrix. So where did I go wrong? And then I kept going, backtracking my steps until I found that arithmetic error. And you should hopefully eventually get good enough to where you're doing the same. Okay, so lots of stuff in this video, right? I mean, it was the same procedure over and over again. There's a lot of stuff to do. All right, so first, Remember, is a matrix symmetric? All right, if the matrix is symmetric, then it is orthogonally diagonalizable. Right, then find the eigenvalues of that matrix, find the corresponding eigenspaces, right, and then also a basis for each of the eigenspaces. And then you're going to use Gram-Schmidt maybe. If there's more than one vector, then they're not already orthogonal. Use the Gram-Schmidt procedure to take each separate eigenbasis and transform it into an orthonormal set, right? An orthonormal eigenbasis. And then you take each of those orthonormal vectors in the orthonormal bases and make those the columns of some matrix, which you can call P. And that matrix where the columns are those orthonormal basis vectors, like this P here, should be an orthogonal matrix such that P transpose times A times P is equal to a diagonal matrix, where down the main diagonal are the eigenvalues of the matrix A in the same order that you put the column vectors in the matrix P. All right. So again, once more, I apologize for the arithmetic error. It happens to the best of us. But everything, all the structure, all the procedures, everything was correct. All right, except for that one tiny little error, which I did catch. And again, I'm hoping you get good enough to where you can see your mistakes and go back and be able to fix them. Right? Always check your work. Always verify things at the end. And that's another big lesson to come out of this end of this video. Because again, I'm too lazy to edit. All right. So thank you for watching. Hopefully it wasn't too much of a. Hopefully it didn't confuse you too much at the end there with the little error. All right. Hope I fixed it in a way that made sense. And yeah, just hope you enjoy practicing problems of this nature where you're given a symmetric matrix and asked to find an orthogonal matrix that orthogonally diagonalizes it. Thank you very much for watching.